The open loop transfer function of a unity feedback system is given by G of S H of S equal to 5 upon S multiplied by S plus 1 multiplied by S plus 2. Draw the Nyquist plot and hence find out whether the system is stable or not. In this case, because of this S, the Nyquist contour is different. What is the Nyquist contour? Nyquist contour is contour C1. It varies from 0 plus to J infinity. That is C1. Then a semicircle of radius infinity from R e power j theta. R tends to infinity and theta varies between pi by 2 and minus pi by 2. That is the second segment C2. The third segment is from minus j infinity to 0 minus. That is the third segment. In this sum, because of this S, S is at the origin. That is 1 by S means a pole at the origin. That should be excluded because this Nyquist contour must be analytic. Analytic means it should not pass through any of the poles. That's why we have to exclude that pole. So draw a semicircle about that pole of radius epsilon, similar to C2. Its radius is epsilon e power j theta, as epsilon tends to 0 here. There is R tends to infinity, here epsilon tends to 0, and theta varies between minus pi by 2 to pi by 2. That is the difference. So this segment is called C4. We have to map C1, C2, C3, and C4 on the function G of S, H of S. So if you map this on G of S, H of S, what we will get, we have to see. So for that, the first step is we have to consider the mapping of C1. We have to consider the mapping of C1. C1 means omega varies from 0 to infinity. It is nothing but a polar plot. That's why we have to find G of j omega equal to 5 upon j omega plus 1, j omega plus 2. Modulus of G of j omega equal to 5 upon omega square root of omega square plus 1 square root of omega square plus 4. Angle of G of j omega equal to minus 90 for S. For this one, minus tan inverse of omega minus tan inverse of omega by 2. If we substitute omega, when omega tends to 0, the magnitude modulus of G of j omega tends to infinity. Angle of G of j omega equal to, if you put omega equal to 0, you will get minus 90. When omega tends to infinity, G of j omega, because there is no polynomial in the numerator, the only denominator polynomial, that's why it tends to 0. Omega tends to infinity, it tends to 0. Angle of G of j omega equal to 3 angles. This is minus 90. Omega tends to infinity means this also becomes minus 90. This also becomes minus 90. Therefore, minus 270. There is no numerator polynomial. That's why the polar plot the plot for this is, it starts at minus 90, infinity, j minus j infinity. It starts at infinity and it reaches 0 at 270 degree. That's why the plot will be looking like this. When omega equal to, omega tends to infinity, it reaches here. Real part of g of gh, real part of gh. This is real part, imaginary part of gh. So that the plane is gh plane. The plane is gh plane. This is in s plane. This is in s plane. So now we did the mapping for C1. Now we have to do the mapping for C2. That is mapping for C2. Mapping for C2. C2 is what? C2 can be mathematically defined as, C2 can be mathematically defined as R, R tends to infinity e power j theta, and theta is lies in between pi by 2 and minus pi by 2. This is the definition for C2. This we have to substitute in g of j omega. G of j omega equal to, the magnitude is here 5 upon s. S means r e power j theta, r e power j theta plus 1, r e power j theta plus 2. If you take r e power j theta outside, what you will get is r cube e power j3 theta. Here 1 plus 1 by r e power j theta, 1 plus 2 r power e j theta. As r tends to infinity, here we have to include that limit r tends to infinity. Infinity. That is equal to this tends to 0. This is also tends to 0. This only this alone is there. R tends to infinity, it becomes epsilon, as epsilon tends to 0. Or you can put simply 0 e power minus j3 theta. Therefore, the angle varies from 3 times 90, that is minus 272, minus 272, minus 272 plus 270. It varies like that. So it is the mapping is like this. So anyhow, it is a point at origin, but its angle only varies. Its angle alone is varying. Therefore, its angle varies from 272 minus 272 plus 270. A point at origin. It is nothing but a point at the origin. Now mapping of C3. C3 is what? C3 means omega varies from minus infinity to 0 minus. So it is, the mapping is mirror image of mapping of C1. Therefore, what is the mapping of C1? Mapping of C1 is this. This is mapping of C1. it will be a mirror image, means it will be like this. This goes to J infinity. Now we have to do the mapping for C4. Mapping of C4. Mapping of C4. C4 means what? Epsilon, as epsilon tends to 0, e power j theta, theta varies from minus pi by 2 to plus pi by 2. Theta varies from minus pi by 2 to plus pi by 2. If you substitute here, g of j omega equal to as omega tends to epsilon e power j theta equal to 5 divided by epsilon e power j theta, epsilon e power j theta plus 1, epsilon e power j theta plus 2. So as epsilon tends to 0, this tends to 0, this also tends to 0. The only 1 by 0, this becomes 1, this becomes 2, 1 by 0. Therefore, 5 upon 0 e power j theta, or 5 by epsilon equal to infinity e power minus j theta. Theta varies from minus pi by 2. Theta varies from minus pi by 2 to plus pi by 2. Here, because of this minus sign, it is radius of infinity. The mapping is radius of infinity. Mapping is radius of infinity, and angle varies from plus pi by 2 to minus pi by 2. This is the Nyquist plot. This is the Nyquist plot. So, what is the Nyquist plot? Nyquist plot is this is for C1, segment C1 up to minus j infinity. This is for C3. This is up to plus j infinity. The mapping of C1. This is mapping of C1. Mapping of C1. This is mapping of C3. Mapping of C2 is a dot at C1. This is mapping of C2. Then this is mapping of this is mapping of C4. Its radius is infinity. It varies from pi by 2 to minus pi by 2. Its radius is infinity. Its radius is infinity. This is the mapping. So now we have to find where it intersects the real axis. To find that, let this point be A. To find the point A, that is intersection with the real axis, that we have to find. To find the point A where it intersects the real axis, we have to consider the transfer function g of j omega equal to 5 upon j omega plus 1, j omega plus 2. So multiply the complex conjugate on both sides, numerator and denominator. What you will get? 5 complex conjugate of this is 1 minus j omega, and for this 2 minus j omega. If you multiply this, this j will come here, minus j. If you bring this j numerator, you will get minus j omega multiplied by omega square plus 1, omega square plus 4. So this is, from this we can write minus j5 what you will get? Minus omega square minus 3j omega plus 2 plus 2. So what you will get upon omega square plus 1 omega square plus 4. If you bring equate imaginary part to 0 to get point of intersection with the real axis, because at this point imaginary part of omega equal to 0, imaginary part of g of j omega, imaginary part of g of j omega equal to 0. That's why we are taking the imaginary part out and we are equating this to 0, minus j5 and minus omega square plus 2 equal to 0. Or omega square equal to 2 or omega equal to plus or minus root 2, plus or minus root. So for this we have to find modulus of g of j omega. Modulus of g of j omega 5 divided by omega root 2 omega square root of omega square plus 1, 2 plus 1 square root of 2 plus 2, that is equal to 0.833. Therefore the point of intersection A equal to minus 0.833. A equal to minus 0.833. Therefore, the Nyquist plot doesn't encircle minus 1. Minus 1 is here. Minus 1 is here. It doesn't encircle minus 1. Therefore, n equal to 0. What is P? Consider this transfer function. Here n equal to 0. P equal to 0. Therefore, Z equal to P plus n. That is also 0. Therefore, the given system is stable for a gain of 5. The given system is stable for we have to write given system is stable for the gain, static gain 5. What is the range of k for stable? That is range of k for stable is, here it is 0.833. If you divide this by 5, because we have to take k equal to 1 to find the gain margin. So, but k equal to 5 here, that's why we have to divide this by 5. Therefore, A equal to 0.833 divided by 5. How much? 0.833 divided by 5. 0.16. Therefore, gain margin equal to 1 by modulus of A, that is equal to 1 by 0.16, equal to how much? 6.2. Therefore, we can increase a gain of 6.2. Already it is 5. If the value is above 6.2, definitely it will be unstable. Sketch the Nyquist plot for a system with open loop transfer function g of s h of s equal to k multiplied by 1 plus 0.4s multiplied by s plus 1 upon 1 plus 8s multiplied by s minus 1. Determine the range of k for which the system is stable. First of all, we have to get the Nyquist contour. This is the Nyquist contour on S-plane. It goes from 0 plus to j infinity. That segment is called C1. The second segment is called C2. Its radius is R. R tends to infinity, and theta varies from pi by 2 to minus pi by 2. So it is a semicircle of radius infinity. It goes up to minus j infinity. That segment is called C. The next segment is called C3. It goes up to 0 minus. So it consists of 3 segments, C1, C2, C3. We have to do mapping of this 3 segments on G of S, H of S, so that we will get a plot on GH plane. That is GH plane. That is called, this axis is called, x-axis is called real part of GH, and y-axis is called imaginary part of GH. Now we have to do the mapping of C1. First, let us do the mapping of C1. To do the mapping of C1, consider what is the C1. What is the value of omega? It varies from 0 plus to infinity. What is G of j omega? GH of j omega equal to K multiplied by 1 plus 0.4 omega j 0.4 omega multiplied by 1 plus j omega upon 1 plus j 8 omega multiplied by minus 1 plus j omega. What is modulus of GH of j omega? That is equal to K square root of 1 plus 0.16 omega square root of 1 plus omega square upon 1 plus 64 omega square multiplied by 1 plus omega square. 1 plus omega square getting cancelled. Therefore, angle of GH of j omega equal to tan inverse of 0.4 omega plus tan inverse of omega. These two for numerator. For denominator, you will get minus tan inverse of 8 omega minus tan inverse of omega by minus 1. Real part is minus 1. Therefore, real part is minus 1. That's why this can be written as, this is in the second quadrant. That's why it can be written as minus of tan inverse 180 minus tan inverse of omega by 1. Now, when omega tends to 0, what you will get here is modulus of GH of j omega equal to K. Angle of GH of j omega equal to, this is 0, this is also 0, this is also 0, this is 180. Therefore, minus 180 degree. When omega tends to infinity, what you will get? GH of j omega equal to, you will get infinity by infinity form. So, as a limiting case, you have to find the polynomial and you have to differentiate the numerator denominator with respect to omega. Finally, as a limiting case, you will get 0.05 K. Angle of GH of j omega equal to, for this you will get 90 plus 90, for this plus 90, minus 90, minus 90. Therefore, angle is 0. So if you tabulate all these values from omega equal to 0 to infinity, you will get this table. For intermediate values, if you find for 0.5, you are getting 0.24 angle minus 191. For 1, you are getting 0.13 angle minus 151. For 5, you are getting 0.0559 minus 47. For 10, you are getting 0.05 angle minus 24. These are all you are getting by substituting the magnitude of omega equal to 0.5, 1, 5, 10, and 100. These are the values you got. You notice that initially it goes above 180. That's why it goes above negative real axis and then come down negative real axis. That's why the approximate plot is looking like this. The approximate plot is looking like this. So the initial value is K 180, that is minus K. After that, angle increases. That's why it goes up. Then angle decreases. Finally, angle comes to 0, that is 0.05 K. Now, this is mapping of C1. Here, we have to find this point of intersection with the real axis. To find this point of intersection with the real axis, what we have to do is, we have to equate the imaginary part of GH of j omega equal to 0. That is, if you multiply the complex conjugate of denominator with numerator and denominator, you will get 1 plus 64 omega square, and multiplying the numerator and denominator by complex conjugate of denominator, 1 plus omega square, and numerator you are getting K multiplied by minus 1 minus 17.4 omega square plus 3.2 omega power 4 plus J 5.6 omega and minus J 14 omega cube. So these two are imaginary parts. These two are imaginary parts with K. Therefore, imaginary part of GH of j omega equal to 5.6 omega minus 14 omega cube multiplied. This is the imaginary part. We have to equate this to 0. Therefore, omega multiplied by 5.6 minus 14 omega square equal to 0, or omega equal to 0, 0.632. These are the two values we are getting. For this value, we have to find modulus of GH of j omega when omega equal to 0.632. That is, if we substitute on this modulus of G of j omega here, if we substitute here, what you will get is 0.2K. You are getting 0.2K. Therefore, the point of intersection with the real axis, this point is 0.2K. Now we have to do the mapping for C2, mapping of C2. Mapping of C2 is omega equal to R e power j theta. R tends to infinity, and theta varies from pi by 2 to minus pi by 2. For this, what is G? What is G of j omega, H of j omega equal to what you will get? Substitute R e power j theta omega. So K 1 plus J 0.4 omega equal to R e power j theta, and 1 plus J R e power j theta upon 1 plus 8J R e power j theta and 1 plus minus 1 plus J R e power j theta. If we take r e power j theta outside, g h of j omega equal to r square e power j 2 theta, you will get outside r square e power j 2 theta, and here you will get 1 plus j 0.4 divided by r e power j theta. 1 by r e power j theta plus j plus j. The denominator 1 by r e power j theta plus j8, 1 by r e power j theta plus j minus 1 by r e power j theta plus j. That's all. So r tends to infinity means these are all become 0. R tends to infinity means these are all become 0. Therefore, gh of j omega equal to this r e power j theta also getting cancelled. Therefore, finally you will get j 0.4 multiplied by j upon j8 multiplied by j. All j getting cancelled. Therefore, you are getting 0.4 divided by 8. In addition, you are having k. In addition, you are having k. That is equal to 0.05 k. So, the mapping of C2 is nothing but a point at 0.02 k with that's all. Therefore, the mapping of C2 is a point at 0.05 k. That's all. Now we have to find the mapping of C3. That is omega varies from minus infinity to 0 minus. For that, it is mirror image of mapping of mirror image of mapping of C1. That's why it is nothing but the mapping is mirror image of mapping of C1 means it will be like this. That's all. So it goes this way, then it stays here for omega equal to infinity, and then it returns like this. That's all. So now we have to discuss the stability of the system. So this is the mapping. There are three possibilities. One is the -1 may be here, or the -1 may be here, or the -1 may be here. There are three possibilities. When -1 will be here, the case one is -1 will be there if k is between 0 and 1. Case 1. In that case, if k is lies in between 0 and 1 means this point, this minus k will move between 0 to -1. In that case, for this range of k, the system is n equal to what? N equal to 0. No encirclement with the -1. What is P in this case? In this case, P is one pole is on the right hand side. Therefore, number of poles on the right hand side, P equal to 1. One pole is on the right hand side. Therefore, P equal to 1, N equal to 0. Therefore, Z equal to P plus N, that is 1 plus 0 equal to 1. One closed loop pole is on right hand side, and the system is unstable. That's all. Case 2. That is second case. That is -1 is not here. It means k is greater than 1. K is greater than 1. K is greater than or equal to 1. And but this point is less than 1. Therefore, what is that point? Greater than 1. 0.2 k equal to 1 means k equal to 1 by 0.2 equal to 5. But k is greater than 1 but less than 5. In that case, minus 1 is lies in between minus k and minus 0.2 k. Minus 1 will be lies in between minus k and 0.2 k. In that case, n equal to what? N equal to 1 plus 1 because it is in the clockwise direction. And p equal to what? P also equal to 1. Therefore, z equal to p plus n equal to 1 plus 1 equal to 2. Therefore, two closed loop poles on the RHS and system is unstable. System is unstable. Then case 3. Case 3. Case 3, what it says? If case 3 is, if minus 1 is here means 0.2 k is greater than 1. 0.2 k is greater than 1. That is, k is greater than 1 by 0.2, that is equal to 5. Case 3 is minus 1 is between 0.2 k and origin. So it means the k should be greater than 5, greater than or equal to 5 and less than infinity. In that case, it is the encirclement is in the anti-clockwise direction. Therefore, n equal to minus 1, but p equal to 1. Therefore, z equal to n plus p, that is equal to minus 1 plus 1 equal to 0. Therefore, the system is stable for this range of k. That's all. That's all about this.